Okay. Okay, let's start this class. Yeah. Yeah. Okay. Yeah. Yes. Yeah, discuss after this class. Okay, let's start this class. Today we will talk about ADC. Have you ever heard this before? No? Never?
The digital conversion.
Yeah. I think if you did had the microcontroller, microelectronics, yeah, you know this one. A stands analog signals, D digital signals. C converter, change transfer like that. We try to transfer the signals from analog form to the digital signals, and then the ADC is very important for electrical engineering thing. Yeah. Let's talk about why it is very important. Okay. Before we talk about that, what is the analog signal?
Everyone's like the things that you can see it, like Fox, like a
That was like a human input.
yeah.
Huh?
Human input.
Human input. Did you see human input?
Yeah.
Oh, yeah, sort of. Yeah.
Like a physical input, like nobody analog.
Yeah, I think yeah. It's an example. Yeah. Like a human input, sort of like that. Yeah, actually, like in the real world, most Will said, most physical quantities change continuously. We can call that analog signals, such as here, like the temperature, like the time, like the sound, radio, some other things, yes, and so on, pressure, like that. And actually, with a certain time frame, those physical quantities can have unlimited values. Actually, you can see when you see this time in the phone, actually we see it is it's not continuous, it's not unlimited values, am I right? But in the real world, the time, you can see the time as a time passing. Actually, it is unlimited values. Yeah, you can goes to a limitation. You can get the smallest as possible. That makes sense to you? Yeah, this is we call it a quantity, physical quantities with a certain time frame. Those physical quantities can have unlimited values, and also those physical quantities, we call it analog signals. Do you know why we call it analog signals? Actually, I think I talked about this in microelectronics. Do you remember? Yeah, because we all didn't do that. Yeah. Do you know why we call it analog signals? Yeah, actually, yeah, the analog signals we have temperature, sound, pressure. Do you know why? Let me show you this image, and I'm trying to guess why we call those quantity, physical quantities, analog signals. Analog, what does that mean? Yeah, in the English word, what does analog mean?
Old.
Old. Okay, really? Actually, I'm not very familiar with the English word. So analog means old? Oh, okay. Oh, so it's a very traditional word like that. Yeah. I think you got that, Merriman. You can see when we talk about the temperature. Yeah, we can our some words pop up in our mind the time. We know minutes, seconds, hours. For the temperature, that the degree. For the pressure, some other values. Am I right? Yeah, but these things we just our human put this unit to the specific physical quantities. But in the real world, in the natural things, the temperature is just a temperature. Am I right? We can call it temperature. We also can eat A, B, C, D. Am I right? Yeah. So actually, you can see all those physical quantities we have. If we want to get these physical quantities, what things we usually use? If you want to measurement the temperature, if you want to measurement some pressure or get some time, like if you want to like measurement the time, you need to use clock. Am I right? For the temperature, you use temperature measurement equipment. Yeah. What's the whole name? Like what's the one word for those things? Yeah, sensors. Yeah, you know, like all these things can be measured by a sensor. Am I right? Actually, those sensors measure those things. It just give you a value, like with the specific unit. This process is like a simulate. Yeah, I just want to simulate the real world's like a specific value in a specific value of things. Like for example, the temperature. Usually in the real world from the 30, maybe in the Arkansas, maybe below 30 some, for example, from 30 to the 100, like that. Yeah, I'm right. Yeah. So which means we just we just use sensors to simulate these value physical quantities to a specific range. Am I right? Yes. The other thing is a similar thing. The moisture, like the light, the motion, the noise, something. We just use some sensors to simulate these values and put these things in a specific range. Yeah, this is just like the analog. Actually, as I know, like I just do some research. It's kind of simulate. The word is have the meaning simulate thing. I don't know. I don't know if it is right. Yeah. So then we call these signals analog signals. Actually, the analog signals, actually, we use the sensors. The sensors give us some specific values, am I right? But the real world, those physical quantities, actually, it has unlimited values, am I right? For example, in this room, if we want to measure the temperature, actually, every seconds, every milliseconds, every like no matter how small the time is, you can always measurement the temperature. Am I right? Actually, the temperature in this room is analog signal. It is unlimited values. Am I right? But we use sensors. We just measure this in a specific time. Am I right? Yeah. So it kind of like this process we call it quantitative like a process we will talk about later. And then this is analog signals. Yeah, you just try to remember the analog signals is just try to use sensors to measurement these signals. Actually, this signal, like basically, it is unlimited and it is continuously. Does it make sense to you? Yeah. Okay. Then, like correspondingly, we have the digital signals. Yeah. What is digital signals?
The stuff the computer reads, like the zeros,
Yeah.
ones, highs, lows.
Yeah. 0, 1, like high, low. Yeah, and we talk about this in last class. Actually, the micro, like a controller, like the PQW, always deal with digital. Am I right? He knows the digital. Yeah, like we use 3.3 as high. We use 0 as low. Am I right? So which means your microcontroller is just reads the voltage around 3.3, all the voltage around 0. And 3.3 means 1, and 0 means 0. Am I right? Yeah, so which means your microcontroller, you just remember, it only reads high, low, off, on. Yeah, it will not read some other values. Maybe around 3.3, maybe from 2.4 to 3.3. But yeah, around like that. Yeah. And you can see, usually like the digital signals, you can like actually you can display it in the oscilloscope. If you, yeah, we have already done some labs in the microelectronics. If you took electronics or microelectronics, you will know the digital signals can be represented in a oscilloscope. Actually, in one following lab, we will like try to observe some signals in the oscilloscope, but not today's signal. But you can observe these digital signals in oscilloscope. And for the digital signals, we know it is high on, like high, low, off, on, 1, 2, 1, 0. Yeah, that makes sense to you? Okay. Then let's talk about how can we like convert the signals from the analog to the digital. Yeah, actually I talk about, yeah, you can see this is the like analog signals. For example, the temperature in this room, am I right? This is time. As the time passing, every time you have temperature, am I right? Yeah, but you can see if we want to like try to use computer to represent these signals, and we need to transfer it to the digital because the computer only reads the like digital signals. Am I right? Yeah, but how? Firstly, this is a continuous like signals, but just remember we don't the computer don't deal with the analog signals because you can see unlimited time has unlimited value. The computer cannot deal with like unlimited values, and I think it is like meaningless. Yeah, for a computer, it's not efficient. Am I right? And then the first step is sampling. What does sampling mean? Do you remember? Sampling. Yeah. Do you remember what is sampling? Does anyone tell me what is sampling?
When you sample one output,
Sample what?
output,
Output?
just one at that specific time.
Yeah. Yeah, that's right. Like this is what we talk about in signals and systems. Yeah, actually you can specific get you can get the specific value using some like import function, step function like that. Yeah, actually this it has the same idea here. For example, this is the original, for example, this is T. For example, let's try to talk about the temperature. And this is this room temperature from from 0, for example, like 0 12 a.m. Today the temperature is similar like and then continue to the infinity. Yeah. Yeah, for example, this is like temperature in this room because the temperature will not change a lot of time, right? So I just, and then you can see our computer cannot deal with, for example, let's try to make it. Yeah, our computer cannot deal with analog, so we just try. The first thing is sampling. Yeah, just like the question talk about, we just get the specific value, right? So then sampling, which means we want to try to get the specific value from the original one. But there is a condition. What is the condition? After sampling, what is the condition? I see that? Oh, yeah. Do you know what's the condition? If you want to, this is the original one. After, let me ask you a question. After sampling, like the signal should similar with the original one, am I right? Yeah, because the after sampling, the signal still the original signal, am I right? It should not be changed a lot. That makes sense to you. So what is the condition after for the sampling? Actually, there is one important term frequency. We need to get the data in a specific frequency, am I right? Like for example, this is T, which means every second we get a value, or every 0.5 we get a value, or every 2 seconds we get a value, every 1 hour we get a value, am I right? Yeah, so we have the frequency. So for the sampling, what is the condition for the frequency? Okay.
Does it need to be continuous?
Uh,
It can't just like,
yeah, I got you.
right?
Yeah, I got it, but it's not. You mean it should be after you sampling, it should represent the original one. Am I right? Yeah. But you can see if we, for example, this is 1 second, am I right? 1 second, we just take a sample, and that is just very perfectly represent the original one. Am I right? If you use 1 second to get the temperature from this room, am I right? Yeah, but if we use 1 hour, for example, we use 1 hour. Yeah, this is 1 hour, which means we just get this value, 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 this value. All right. similar like that. And then we try to simulate it just similar like this one. Yeah, because you just try to connect two, am I right? So this is just like the value we get. It's similar with the original one, am I right? But if your frequency is like 10 hours, for example, this one, you get a value. After 10 hours, you get this one, which means your sampling single will become this one. So which means your after sampling, your single is now exactly the original one. Am I right? Yeah, which means after sampling, if you have the frequency is too small, it is still not very efficient. Am I right? Yeah, but if you have the frequency is too big, which means you have the you just like get the single. It is not the original one. It is totally not the original. So when you sample it, you need to choose the specific, choose the purple frequency to get your like a value. And the sample, what is sampling? Which means I just try to use the specific frequency to get the value. You can see here, this is the first one, this is the second one, this is the third one. You can see the duration time is the same. That makes sense to you? Yeah. Okay. Then we have the quantification process. Like after, you can see after you sampling, you get this value, this value, this value, which means if you after you sampling, your signal should become this one. It's not the original one. It's just the red line. Sorry, it's just this one. I'm right. The red line. Yeah, but it's similar with the original one. I'm right. It can represent the original one. That makes sense to you? Yeah. And after this, there is a quantification, like a process. What is quantification? Have you ever heard this before? What is quantification?
It's just rounding.
Huh?
It's rounding.
Grounding?
Like rounding.
Yeah, kind of like it's grounding, but for what?
So you can convert the whole numbers to the binary.
We haven't like reached to that. Yeah, but yeah, that's a good guess. Actually, you can see. For example, this is temperature. I'm right. We want to measure. We just like every 1 hour we get 1 hour. We measure one time. I'm right. So this is for example, this is 8 a.m. This is 9 a.m. to like 10 a.m. 11 a.m. I'm right. But how about 9:30? How about 8:30? What's the temperature? Huh? What? Cold. Well, yeah, we just measure a temperature like from 8 a.m., 9 a.m., 10 a.m., 11 a.m. I'm right? 10 a.m., 11 a.m., 12 a.m., 12 p.m., yeah, 1 p.m. Yeah, how about 8:30, 9:30, 8:50? Predicted? Yeah, but how? How can we predict? You need based on this value, am I right? Because after sampling, you just have this value. That makes sense to you? Yeah, you just lost the original one. So which means 8:30, like 8:30, maybe it's just a half. You can decide a rule. It will close to this value. I'm right. For example, this is 8. This is 8:30. Let's make a rule. It will close to this one. I'm right. And 9:30, it close to this one. And 8:15. Let's because it close to this value. So let's the 8:50 value is this one. Am I right? That makes sense to you? Yeah. So which means we need to do a quantification. Which means for the time, if you want to the temperature for 8:30 or 8:15, I can tell you, and the value is just like the closest value. We have already get. That makes sense to you? Yeah. This kind of the quantification. Yeah, we will talk about later in today's lab. Yeah, and after quantification, we have the 8 a.m., 9 a.m., like 10 a.m., 11 a.m. But this value 200 like 92, about 100 like 20 82 23. the computer, if the computer want to deal with, if our microcontroller want to deal with, we need to transfer it to the digital. Am I right? Because the microcontroller, like I said, it just reads 3.3 and 0 or 0. Am I right? So we need to give it, or it is, we need to transfer it to the digital. Like 200, 0, oh, this is 202. Yeah, then we transfer it to the binary number, this one. And 100, like 23, we convert it to the binary number, this one. And then try to create this binary number to the microcontroller. And then the microcontroller will know, at 8 a.m. you have this temperature. At 9 a.m. you have this temperature. At 10 a.m. you have this temperature. Does it make sense to you? Does it make sense to you? Yeah, any question so far? Any question? Yeah, okay. Then I will continue to talk about that. And then you can see this one. This one is just like how can we produce 1 0 in a circuit? Yeah, actually, this is we talk about this in microelectronics. This is a specific circuit, transistor logic TTL circuit. Actually, in this circuit, we can use this circuit to transfer the voltage to the digital. If your voltage around 5, it is then it will be 1. And if your voltage is around 0, it will be 0. Yeah, we actually do many labs in microelectronics. Actually, there are some circuit you can use the circuit to try to transfer the analog to the digital. Yeah, that makes sense to you? Yeah, and then actually when we transfer the analog to the digital, there are some rules. Yeah, for example, in the circuit and the voltage, the high voltage is 5. We just consider 5 is 1, 0 is 0. I'm right. And but in the real situation, like your output voltage, maybe it's not 5. Yeah. So we just make a rule. If your voltage greater equal than 2.4, and then it will be 1. Otherwise it will be 0. Am I right? And this is the other situation because based on your circuit. For example, do you remember when we this is TTL circuit? We can use TTL circuit to try to compare different inputs and then try to decide, oh, this is 0 or 1. Am I right? Yeah, but you can see we also can create this circuit using op-amp. Am I right? The op-amp will give you the other situation. Yeah, this is just a different situation. Have different for this situation greater equal 2, and it will be considered as 1. Otherwise, it will be if it is smaller than 0.8, it will be 0. Yeah, that makes sense to you? Any questions so far? Yeah, let me also. This is for the other situation. We consider 3.3 as 1 for our pico W. We know we use 3.3. Am I right? And then 0 consider 0 as 0. But this is just a range. If it is greater than this value, it will be 1. We consider it 1. If it is smaller than 0.4, it will be considered as 0. Yeah. Okay. Let's sum it a little bit. Yeah. Which means for the microcontroller only reads a high, low. Am I right? 3.3 or the 0. Am I right? But you can see our sensor can sense the temperature, can sense the pressure, can sense many things. Am I right? But these things, they have the specific value. Am I right? But this specific value, if the microcontroller want to deal with it, we need to transfer it, convert it to the digital. Am I right? And then this is how can we transfer the analog to digital? And in the theory, yeah, firstly sampling and then quantification, and then try to digital it, convert it from the decimal to the binary. That makes sense to you? Yeah, and then this is some circuit. This circuit can help you to for example, how can when your when the microcontroller will read 0, when it read 1, am I right? And then this is just some rules. If your voltage greater than 2.4, the microcontroller will consider 1. If it is smaller than 0.5, the microcontroller consider it is 0. That makes sense to you? Yeah, and then the microcontroller will read the data successfully. Yeah, this is today's lab. Okay, let's try to review today's lab. Yeah, for the lab 4, and what we will cover, what an ADC actually does, and yeah, you will tell me after this lab, and how a microcontroller reads analog voltage. Actually, you can see, like I said, the microcontroller only get the digital signal, am I right? But how can the microcontroller read the analog voltage? And then serial communication with a sensor chip. Actually, for our activity 1, and we will try to use the Pico W, try to communicate the POW will communicate with the sensor chip and using serial communication method. Actually, here the communication. Are you familiar with that communication thing? We know the Pico W can communicate with many things, am I right? Many devices, and there are different protocols. Do you remember that? Do you know what are those? You know? Do you remember? Actually, homework 1, I just let you. Yeah. That's one. I2C, SPI, UTAR, yeah. This is just a different communication method. But today we will try to communicate with the sensor chip using the serial communication method. Yeah, and then in the following labs we will use the other communication method. And today's lab also cover convert binary to the voltage. Yeah, how can we convert the binary to the voltage? Yeah, because you can see the Pico W read the voltage, am I right? Different voltage, but a different voltage for us it's just a specific value. For example, 2.2 voltage and 3.3 voltage and 2.5 voltage. But for the microcontroller, like I said, it just reads the digital number, am I right? 0, 3.3, high, low. But then how the Pico W reads the voltage? And then lastly, we will compare external ADC VS internal ADC. Actually, the Pico W provide ADC directly embedded in the Pico W. Also, we will use a chip a external chip to implement ADC. Okay, this is lab 4 we will cover, and then let's talk about the motivation. We know your microcontroller is digital. Like I said, no matter in your microcontroller, it is always a 3.3 or 0. You can see your pin. You have already finished 3 labs, am I right? Yeah, but you can see your pin is always read 3.3 or 0, on, off, high, low, am I right? To try to let on the LED, try to read the button. Yeah, the button also, yeah, and but the real world is analog. Like I said, the temperature, the pressure, anything in the real world, it is analog. So if our Pico W wants to read these analog signals, how can we do that? Yeah, this is some examples. So we need a translator. Yeah, this translator is ADC. We try to transfer the analog to the digital, and then the Pico W can read it successfully. Am I right? Yeah. So this is what we will talk about. We will do in today's lab. Okay. Then let's talk about what does an ADC do. Yeah, ADC mirrors voltage and returns a number. Yeah, this is, for example, this is a 0. In our lab, for example, our voltage is 0. Then you will find your Pico W's output is 0, 0, 0, the binary number is this one. and the decimal you can transfer it to. You can after transfer the binary to the decimal, it is 0, and then like 1.65 volt, and it is this one. It's 128, and 3.3 volt. It is this one. It's 255. So did you notice? This is the voltage, like the lowest voltage, the pico W can the lowest voltage, and this is the highest voltage. I'm right. During this voltage, and it can be represented using binary from this value to this value, which means for the decimal from 0 to 255. Yeah, and then let's talk about for our pico. We know like the voltage the pico W can provide is from 0 to 0.3, am I right? Yeah, so which means like for the voltage, we only like if you use pico, you only can represent 0 to 3.3, am I right? Yeah, that I will talk about like why this is very important like for today's lab. Okay, actually the ADC does not measure continuously. It quantities the signal. Like I said, you can see it involve a term resolution. You can see for the ADC we know like it is for the ADC like chip we use today TCL we will use the chip called TLC 0831, and this is a 8-bit like a ADC chip. 8-bit, what does that mean? Yeah, I have already given you the result, like answer. 8-bit, which means it can represent like a 0 to 3 power 3 like power 8 number. Am I right? This is 0 for the decimal. 0 to 255. Am I right? 0 to 255. So it totally it will 256 levels. Yeah, from 0 to 255 is 256 levels. Am I right? Yeah, and then this is the resolution. Like a ADC converter can represent the resolution equal V max, like a divide 2 power n. This n is just here. For this chip, it is 8. Am I right? So the resolution for our circuit, the resolution is what? Do you know? Yeah, that's right. It's around 2.213 volt. I'm right. What does that mean? What does that mean? I can
That be the smallest like increment of measurement that's like the difference between 2 points.
Yeah, that's true. That's true. Like if your voltage is smaller than 2 like 0.013, what will happen? Huh? Crappy?
It'll get rounded like.
Oh yeah, rounded. Yeah, that's true. Which means if your like a voltage during 0 to 3.3, like 0.013 volt, and your resolution is the same with this one. That makes sense to you. Am I right? Yeah, and if your like voltage is from 0.013 to 0.026, which means it will go to the other level. Does that make sense to you? Yeah, it depends on what's the rule for us. Am I right? Yeah, this is like a resolution. Okay. Yeah, which means our smallest detectable charge is 30 millivolt. Yeah, we can detect small voltage smaller than that, but the result will tell you, oh, this is 30 millivolt voltage. Am I right? Yeah, it will not tell you, oh, this is 12 millivoltage. It is not a 10 millivoltage millivoltage. That makes sense to you? Yeah. Okay. Then let's talk about the activity 1, the TLC 0831 chip. Yeah, this is our chip look like. It's very small. Yeah, you will know that. And this is an external ADC chip. And we will try to connect it with the Pico W as an external like a chip. Yeah, and then this is this chip's feature. It is 8-bit resolution. I have already talked about what is resolution. It is a series output, which means one time it only can read one date. Yeah, after this lab, you will know that. Yeah, and then it requires clock from Pico. Yeah, you can see here. There is a clock signals here, which means you need to give this pin a clock signal, and you can check the code. Yeah, and also it returns data bit by bit, which means it will read the data one time, for one signal clock. Clock signal. Yeah, and then which means the microcontroller must talk to the chip and then finish the binary number read. Yeah, okay, let's continue to talk about the communication concept. You can see this chip, actually, it does not send the data automatically. The Pico must select chip, which means when you want to let this chip work, the Pico need to send this chip a signal. And then after it send a signal to the TLC, like tell it, I need to communicate with you, and the TLC will, okay, let's communicate, and then like the Pico will send a clock pulse, which means I'll give you a clock signals, and it depends when I will read the data, and then it after like the Pico tell the TCL 0831, and it will give the data to the Pico, and the Pico will read each bit. Yeah. In this situation, in this process, the Pico is the controller, the ADC is the responser. Yeah, which is very similar, like two people. Like for example, me and like Mark. Yeah, I just tell Mark I'm the controller. And I tell Mark, I want to communicate with you. And then Mark, let's communicate. And then I tell like Mark, when I give you a clock signal, and then you give for every clock signal, you give me a data, and the Mark will give a data, and then I read the data like that. Yeah. Any questions so far? Okay. And this is like TLC 0831 pins. Actually, it will have 8 pins, but the chip it does look like this. Yeah, it will look like this. Yeah, this one. Yeah, and in the lab instruction, there will be a very like clear details. Yeah, this is a pins like a CS, which means start communication. I just like give CS pin a signal, which means we start to communicate. And then the clock, which means when I will read the date. Yeah. And the do, which means this is a data output of what I will read. Am I right? And this is V in, it's just the analog input because there are some voltage input. Am I right? And this is just for example, from 0 to 3.3, this is for example 1.5, 1.6. And then this do is just like I convert the like 2.2 to the specific like a decimal number, and then I transfer it to the binary number, and this binary number will output based on this pin, do pin. Yeah, and there is a very interesting pin called V in minus. Actually, this is reference all the negative input. Yeah, in our lab, actually you connect this one to the potentiometer, which means when you change the potentiometer, the voltage here is changing. Am I right? Yeah, actually you will notice this V in minus, you will connect to ground. Actually, the voltage we read is now the voltage goes to the V in plus. It is the difference between V in plus and the V in minus. Which means if your V in minus does not connect to ground, you need your like input voltage will not just this voltage here. But here you connect it to the ground, which means the voltage you read for this chip is just because here is 0, am I right? So the voltage is just here. That makes sense to you? Yeah, this is just in our lab, in today's lab, this is just connect to ground, which means the difference here is 0, and then this is just the voltage we read. Yeah, that makes sense to you? Okay. And this is the reference voltage, which means the biggest, yeah, because you can see the biggest voltage I can read in this circuit. Yes, you can see here, this is 3.3, because for our Pico, we use 3.3, am I right? Yeah, okay. Then, but let me ask you a question. Is this voltage will be changed? Can be changed. Yeah, can be changed. Can this voltage change? This 3.3? Probably no. Yeah, and let me ask you a question. What is VDD? What is ground? You can see in our chip, there is a VDD. There is a VCC. VDD is VCC. There is a ground. Actually, you didn't take the microelectronics, but the students took the microelectronics. What is ADD? What is CC or what is ground?
ADC is like power to chip.
Yeah, that's true.
VN is
Input like that.
input.
Yeah, if there is a VCC and ground, what does that mean? What does that mean?
Chip needs a
Yeah, it needs power, which means it is an active component. Yeah, it needs power, then it needs power to run it. Yeah, which means, so here you need to give this power. This is a 5 volt. And this one is a reference, which means the maximum voltage you read in this. Yeah, because this one, this maximum will depends, will decide the level, am I right? Will decide the resolution, because if there is, this is not 3.3, and the voltage will change, am I right? Yeah, so this is just and I tell you, this voltage 3.3 will change, can be changed to some specific value. I cannot any value. You can change it to the any value, but some specific change, some specific value. And I will tell you why we will change this value and what this value can be changed. Okay, then let's talk about the how the TCL 0831 will work. You can see here, this CS is just like the star communication, like a pin. And I just change it from high to low and tell the TCL, Pico tell I will communicate with you. And then after I set this from high to low, and then I will try to read the voltage, am I right? The TCL will read the voltage and transfer the voltage to the binary number. And the Pico W will try to read this binary number when base the clock signals change. That makes sense to you? Yeah, from high to low, and I will read, and from high to low, and I will read the other. From high to low, I will read next that until 8 bits. That makes sense to you? Yeah, this is how the TCL 0831 work. Okay, this is you can see for each bit the clock from low to high to low, and I will read from low to high to low, and I will read the do pin and repeat 8 times, and the result is binary string like this one. Yeah, and you will know in this lab. Okay, and then you can see here. This is the voltage. Actually, you can see when you adjust that potentiometer. Actually, you can calculate the voltage you will read. Here, this is the equation. This is the read data, and this is this read data. Actually, you can see you can use code to print it out. Yeah, because Pico W will read the binary number. Am I right? This binary number actually it can be transferred to the decimal. That makes sense to you? Any questions so far? I think this one you need to calculate by yourself. Yeah, and this real data divide 255 multiple 3.3. It's the voltage you will get, the input voltage you will get. That makes sense to you? Yeah. Any questions so far? Okay, I think after today's lab, and you will understand this deeply. Yeah, so, and now your circuit becomes at a what? You can see your circuit become a what? You can see based on the binary number the pico W can print. Actually, you can get the voltage, the input voltage. I'm right. What's this? What is this? Are you familiar with this thing? No? Actually, it is a digital voltmeter. Yeah, you can like measurement the voltage input, am I right? That makes sense to you? Okay. And then for the challenge, I give you a code, but this code is just similar with the previous one, and there is no function. In the challenge, I want you to try to write some functions for the specific specific function. Yeah. And why the function is very important. Yeah, this is like it will clear, reusable, professional programming. Yeah, and then there is the other challenge for the activity one, which means you need to create a wording system. If the voltage is smaller than 1, greater than 2, and the LED will on, give you this circuit is now safe like that. Okay, and actually we have the activity 2. Activity 2 is that we don't use a chip. Actually, the Pico provide an internal ADC. Yeah, this Pico already have a ADC inside, and the ADC has a high resolution. It is a 2 power 16, 16-bit resolution. You can see the resolution is this one, am right? It's much smaller than like the one we talk about in using the external ADC, am right? So what does that mean? Which means if your voltage is this one, it is one level, am right? And below this value, you have more level can represent this voltage, am right? You can when you try to measurement the voltage, you can measurement here 0.00005. But for the ADC, you cannot. For the chip, TLC, you cannot. Am right? That makes sense to you? Yeah. So this is much more precious. And then this is the like a pin for the ADC, internal ADC. For the internal ADC, there is no clock needed because the Pico has already have that one. Okay. And let me ask you, like there are 3 different ADC pins, am I right? If you observe here, like 0, 1, 2. Did you see that? Yeah. Do you think those 3 are same? Why they are not same? Actually, the function is same, but just remember those 3 cannot work at the same time. Yeah, so, which means only at the one time one pin work. Yeah, so you need to pay attention to that. Yeah, in the future, like labs, all the final project, you need, if you want to use multiple, you need to pay attention. After this one finish use this one, and then next we'll use. Yeah, just remember that. And this is just the ADC and the internal and the external ADC comparison. You can see. One is resolution will be higher, and wearing for the internal it will be simpler, faster, and the learning value will be low. Okay, and this is for the internal measurement sensor. Okay, let's talk about why learn external ADC. Yeah, because real systems will connect some sensors. Am I right? These sensors, like we talk about here. There is 3.3 because the maximum Pico W have 3.3. But in the real time, the voltage is not only 3.3. It may be 5, it may be 12, it may be, yeah, you can see, am I right? So you need an external, like a ADC to try to deal with these signals. Am I right? Yeah, does it make sense to you? Okay, yeah. So for the external ADC, you are learning communication protocols, not just a voltage reading. Okay, And yeah, you will demonstrate today like binary output changes with knob, voltage calculation works, function implementation, safety LED, internal ADC reading. And this is what you need to, after today's lab, you need to know these things. Analog vs digital quantization, serial communication, bit level reading, voltage communication, external vs internal ADC. Yeah. This is today, after today's lab, you need to know. Okay, let's have today's lab this afternoon.
No.